Hi students, in this video we are going to get into the real meat of integral calculus. We're going to look at the fundamental theorem of calculus. Alright, so we've got a few learning goals here. They are quite wordy, but they are really important in really solidifying what we're doing when we're doing anti-differentiation and how that applies to some of the area work we've done before. So we want to interpret the meaning of the definite integral, shown there, as the area under the curve y equals f of x. We want to see and recognize the definite integral as the limit of sums of all of those rectangles, and we want to understand the formula of the integral from a to b of f of x is the antiderivative of f at b, subtract the antiderivative of f of a, and use it to calculate definite integrals. Like I said, very wordy, but the goal of this video is to not just really know those things, but to understand them and actually know what they mean. So, big things to remember. In previous videos, we looked at finding the area under curves using rectangles, and we used this formula here, where we said the area would be the sum of a bunch of rectangles where this was the area. So dx was our distance along the bottom, delta x, and f of x was the height of our rectangles. And so when we multiplied those together, we got the area of a rectangle, and then we added them all together. So that's one thing to remember. When we were finding area using rectangles, that's what this formula means. We also want to remember that capital F of x is considered the antiderivative of f, which we've been working in these sorts of examples here. Alright, so as previously covered, when using rectangles to work out the area under a curve, we worked out that we could get the most accurate answer possible by using lots and lots and lots of rectangles. So comparing this first approximation to this one over here, in number 3 will be much more accurate because the rectangles are much, much smaller. And that is because the width of each rectangle, delta x, is getting as small as possible. The smaller we make that width, the more accurate our area calculation was going to be. But we were only dealing in approximations because no matter how small we made those rectangles, we always had these little gaps at the top. So the question then comes, how can we work out the exact area under a curve? How can we work out the exact area under a curve? By making those widths of each rectangle as small as possible. So what we're going to do is consider some function, a of x, that tells us the area under the curve from 0 to some value of x. So in this situation here, let's call it, so this value here is ax, the area underneath the curve. Let's say we're going up to some point b here. And so this area was actually going to be, let's rub that out, a of b. Okay? But what we ideally want to know is, well, what is a? What is the function I'm substituting b into that gives me an actual area? Now, what we're going to do to consider that is add on a really small area here. And I'm going to call it dA. So remembering back to some of our derivatives work, that lowercase d represents a very, very small change in a. Right? So a very, very small change in our area that I've just added on there. Now, that area I've added on there, dA, comes from adding on a small little bit of width here called dx. Right? And dx again is a very, very small value of x that I'm going up by there. What I'm really wondering is if I'm going to change x by that small amount, and ideally, remember we talked about dx has these ideas of being something that's, getting very, very close to 0. How can we relate this small area that we've gone up by in terms of dx? Well, dA is approximately a rectangle, and if dA gets smaller and smaller and smaller, right, I've made it reasonably big here, this red patch, but if I made dA, that small area, smaller and smaller and smaller, it would look more and more and more like a rectangle. So a rectangle is a good way to approximate this. So we've got this rectangle for dA, its width is dx, its height here is f of x, this x value we've got here. So that height is going to be f of x. Now, how we can write that then is my very, very, very small area, dA, is going to be equal to f of x, the height of my rectangle, times by dx, my width. Now, and this is the significant part when I work this out and make this look a little bit nicer, I can rearrange this. Right? If I divide both sides by dx, I get something like this. dA dx equals f of x. And this result is actually huge. It's quite enormous. You can tell I'm getting quite excited by this. What we're saying here is the derivative of the area function is under the curve f of x, the derivative of the area function is equal to the function itself. Okay, so f of x is the derivative of the area function. Now, if we want to change that around a little bit, we've talked a little bit about antiderivatives and going in reverse. So if f of x is the derivative of my area function, then my area function is the antiderivative of my original function. Now I'm trying to find the area underneath. This is a very important result. So if we want to find the area under a curve, we need to antiderive it. We need to integrate it. Now it's important here we look at where this came from and how this compares to our previous. Right, so what we're saying then is that the area underneath our curve, this area function that we started off with looking at with rectangles, can be changed from an approximation to an exact value by using anti-differentiation. So what we're saying here now is our area function, the area underneath our curve, is the antiderivative of f of x dx between these two values. Now, here we can actually get into a bit more what the notation is for and why we use this notation when talking about the antiderivative. Because what we're technically doing at this point here, as soon as we start finding areas, we're talking about something called integration. And what's integration? Integration is putting a whole bunch of things together. And so what we're doing is we're basically adding up the area of an infinite number of rectangles to try and find the area underneath our curve. So thinking about our example from before, what we've got here in f of x dx, those are the areas of all the rectangles. But all of the rectangles, an infinite number of rectangles, a huge number of very, 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 very thin rectangles to a degree. And then this sign out the front, this S, it is an S because it's a sum. It's a continuous sum. It's basically saying we are adding up, in a summarized sort of form, we're adding up all of these rectangles in a continuous manner between A and B to determine our area under the curve. That's one way you can sort of think about it and understand it, where you've got S as our continuous sum between A and B. F of x dx, we're basically finding a bunch of rectangles and adding them all up to find our area. Now, recall that we said a of x was going to be the area from 0 to some value of x. So if we want to find the area between a and b, like we have in this situation here, we will need our antiderivative, which we'll use with our capital letters, and what we'll say is the area under our curve up to here, right, is going to be f of b. From 0 up to b, that will be f, our antiderivative of b. If we want to find the area from a here up to b here, what we can do is just take our area from 0 up to b, and then we'll take away f of a. So when we want to find our area under the curve between two values, shown here, from our interval between a and b, what's the area under my curve? It will be the antiderivative, or now we call it the integral, because of, like I said earlier, we're integrating, we're putting things together. The integral of f with b subbed in, subtract the integral of f with a substituted in. We now call this a definite integral, because we are actually counting a definitive sum across an interval. So the indefinite integral was just, we had no interval, we were just anti-differentiating and getting some function. Now we've got a definite integral with a definite interval that we're calculating it over, and hence it's called a definite integral. Alright, very wordy in this video, but it's a bit of background and theory to explain basically where the notation of the integral of x comes from, and how the area underneath the curve is directly related to the antiderivative of the function we're looking to find the area underneath.